Episode 6, Interplanetary Travel. You're listening to SPEXcast. Hello and welcome to SPEXcast, a podcast for discussing the science and technology of space exploration. I'm Phil, and joining me today we have TJ.
Hello.
And Anthony.
Hey guys.
And we're going to talk about going from Earth to other planets in the solar system.
Well, the moon, or asteroids. Asteroids are nice.
Bodies in the solar system, I guess.
Okay.
To be perfectly correct. So the moon is the only one we've actually sent humans to, but we sent probes and things all the way to Pluto, past Pluto, and Voyager is on its way out of the solar system. But how do we do that is the question today. And what's the future of interplanetary space travel? So let's talk about the primary method of getting from Earth to other planets. And it's chemical rockets for a lifter stage and then ion engines, right? For long duration stuff.
It depends. Like, the basic physics behind all of it is that you need to change your momentum somehow. Because momentum is always conserved in space. So you have to increase your momentum or decrease it depending on what you want to do. Or you need to increase the components of your momentum vector to get to the place that you want to go. So chemical is a good way. Chemical is a pretty broad category of saying, I mix something together, I mix two things together, or I spray something over a catalyst. It breaks down, it expands, it creates energy. And with the velocity of the particles I create from that expansion, if I point in a direction, I move. So that's one way to make momentum, is to mix stuff together and have it expand. Like, I don't know. Imagine your childhood like, no, Coke and Mentos. That's really good.
Yeah, it's a great example.
Yeah, and you kind of have that rocket nozzle, and you get this stream of momentum out of it. $10 that if you put that like sideways somehow, I don't know, threw the Mentos in and had it spew out, it would go forward. So that's one way. Then you have thermal rocketry, which is pretty neat. You heat something up so much that it expands, and then as it expands, it shoots out one way, and you go in the opposite way.
So an example of that be the steam rockets we mentioned a couple episodes back?
Yeah, steam rockets are pretty awesome. It was done back in the 60s and everything. There's some great documentaries up there, and it's all pretty well known about nuclear thermal rocketry, which is particularly cool because then you don't have to add any energy in. It's just already there. That energy potential is already stored within the nuclear material, and you can just shove whatever you want down into it. It will get vaporized, shot out the other end.
So is that the radioactive decay heats up, the material heats up because when it decays it heats up and then shoots out the back?
No, so the nuclear material doesn't decay. It's whatever you shove into the engine decays. Well, it doesn't decay radioactively, it vaporizes. Yeah, everything can be a gas if you try hard enough. Terrifying.
Yeah, with chemical engines, you bring the energy inside your chemicals and you react them, and then you use the resulting products as your reaction mass. With nuclear thermal and like thermoelectric, you have your reaction mass and then you get your energy from another source. So a nuclear reactor or electric heaters, something like that, and then you pass your mass through that, and that it gains energy through that, and then you expand it through the nozzle.
And then you've got electric propulsion, which is kind of the last one. And that's the whole idea. Instead of heating it up, you use that whole little fact that when you magnetize things like to move away or towards something. And so you take some kind of inert particle, and you charge a couple of plates to get them to fly towards the plate, and you shoot it out that way.
And that's the basis of ion. When people say ion engines, it's...
Yeah, ion engine. Yeah, and
they shoot out charged particles, and that's what propels the craft.
And that's one way to do it. There's a lot of other different ways to do electric propulsion. Like you've got Hall effect thrusters, you've got magnetoresist. There's tons of ways to play around with ionized particles and shooting them. And then you can get even crazier, and you can do stuff like electromagnetic fields. So electromagnetic fields causes forces. That is a change in momentum. So you can push off that with your own magnetic field. I remember an old concept where it's like, I'm going to make a magnetic field, and then I'm going to use that as a virtual solar sail.
A virtual solar sail.
Yeah, but the energy requirements to make that kind of magnetic field so big to impart solar, it's out there. It's out there.
So it would use, instead of a physical sail, it would use its magnetic field to, like, solar wind would hit the magnetic field and push it? Or is it like making its own wave in the magnetic field to surf along?
This was in an old book that I read over and over. It was really pop sci, so pop sci, but the whole idea was, instead of having a physical, like, sail, I'm just going to make a magnetic field that everything passes through, and as it passes through and as particles pass through it, they slow down and impart some of their momentum onto me. It's out there. I've never seen it again, so it probably got shut down real fast, but yeah.
Yeah.
We can talk about solar sails a little bit too. Sorry, TJ?
So I was going to bring up resistor jet rockets, which are part solar electric propulsion, part toaster. That's how I like to phrase it. Where you have heating elements, very similar to a toaster, and you send your reaction mass through that, and they gain the energy through those heating elements. You have a hot gas, and then you expand that gas. And so it's kind of the simple man's solar electric propulsion. It's a lot easier to do than having your ion engines.
I wanted to talk about solar sails a little bit, because I think they're super cool.
Yeah.
And I'm not exactly sure about the specifics, but I know you take a thin film-like structure, put it out into space, it gets hit by a bunch of light and particles and radiation and stuff. And light has momentum too, right? It's energy.
Yeah.
And when it hits...
Vector.
What, you came back with a textbook. What's in that? What?
The good book. Space Mission Analysis and Design.
It's mad.
Other than me making up answers, if I have to double check something.
So yeah, a solar sail, it gets hit by all this radiation and things, and when it gets hit, there's the tiniest push, and if you have a big enough sail, it's like the way the wind pushes sailboats along the ocean. It's a lot more abstract in a way than just a literal wind pushing a cloth sail, but it was a theory for a long time, right? Until and then it was proven by Light Sail. Maybe I don't think it was proven by them, right?
No. I mean, you can see the effect of solar perturbations on vehicles all the time. Slow degradation that can't be described by drag and everything. Light bounces off of stuff, and we know that changes things around. So yeah, Light Sail, I think Light Sail demonstrated it. There's been a lot of solar sail demonstrators, actually, back into, I think, the 80s. I'm going to double check my facts. But yeah, it's been done for a really long time. But, you know, it's great and all. It's really awesome. But it takes so long to do. So when you're paying for a program and you're paying for stuff to actually happen, yeah, sure, it's energy efficient, but you don't want to pay for that the whole time.
Yeah.
Let's see.
The main benefit I see is that it does happen for a long time, but it's relatively constant, so you can be accelerating for a long, long time. And if you keep accelerating, I mean, the payouts it's like having your engine on for years, right?
Yeah, but are you going to pay someone to watch the engine for years?
Yeah.
If I'm frozen, maybe.
It's like those mission costs. So like we talked a little bit about lowering launch costs, but for some of these like big interplanetary probes, the launch cost is a very small fraction of that, like 15-20% of the actual mission cost. And a lot of that is paying people to be at the tracking station, monitoring the satellite every single day, and then when you actually get to your destination, controlling the satellite, processing the data. So those are the really big costs, as well as, you know, actually manufacturing and launching it. And so if you spend more money on the launch and put in a more higher energy trajectory, and you can get there in 6 months instead of 9 months. That's 3 months of upkeep you don't have to pay for, and then you can get to the actual science. So it's all a lot of pros and cons on your trajectory planning.
Yeah, so my favorite thing, formal rocketry, which requires launching radioactive isotopes and then vaporizing your propellant mass as it gets pushed through. Super awesome. There's a phrase called ISP, which stands for specific impulse. It measures how long it takes for like a kilogram of material to burn to provide 1 mutable second change in velocity. And that has one of the highest kind of chemical ISPs involved. And so in comparison, that one's a really high efficiency way to do it. But A, it takes forever. It's really low thrust most of the time. And B, when you actually have to deal with like launching a nuclear device into space, it makes things really difficult.
So as far as what's most widely used right now, how are we getting most of our probes and rovers and things to Mars and to Pluto and things like that?
Chemical.
Chemical how? You said there was a huge range. Like, so I know the major launch stage is all hydrolox, right? And
not always, yeah. So you still have
RP1.
rocket propellant 1, RP1. You have LOX hydrogen. You have LOX methane. There's a lot of different combinations. You can even do Aerojet and like Aerozine 50/50 and all that kind of stuff. And each one of them has different performance characteristics, health and safety standards, stuff like that. Hydrazine is super dangerous, but it's a pretty good little propellant that doesn't boil off over time.
yeah, to say how dangerous it is, it's odorless, and 2 parts per billion of MMH, which is one of the components of hydrazine, can kill you. Parts per billion.
Yeah.
And it's odorless. You can't see it, like you can only see it in large enough quantities that would kill you 10 times over. So.
Yeah, it's interesting. So we're pretty much restricted to chemical propulsion for a lot of these probes, and yeah, you have a pretty wide variety of launch vehicle fuels. So LOX, RP1, hydrazine, stuff like that, and then you'll tend to go with hydrolox for upper stages because you have very good ISP with that, and you can do a lot of the insertion burns with that. However, once you leave Earth's gravity well and you have those very long coast times where you get into weeks, months, years, hydrogen is very hard to store over time, right? Because it's going to absorb heat from the environment. It's going to start boiling off. And so it's pretty much all storable propellants like hydrazine, where you take a hit in the ISP department for ease of storability and energy density.
Right. So now that we kind of have an idea of how we're going to move ourselves through space, do you want to talk about how, like, the craft itself that's going to be traveling? Because I was thinking, if you want to go really far, part of that momentum equation is your mass, right? Mass and velocity and blah, blah, blah. So if you have something that's really, really light, it's easy to send it really far away.
The key aspect is not just the mass, it's the mass ratio between your fuel and your kind of like payload. So the more percent of your starting mass is fuel, the more delta V you have and the farther you can go.
Sorry, Anthony, I didn't catch that.
Sorry, and dry mass, don't forget that. It's the annulled mass. Yeah. Anyways.
In general, a smaller craft can go farther because efficiency, right? So if we want to send people, if I wanted astronauts to travel interplanetary in general, how are we going to do that? I was thinking, like when we went to the moon, we had a multi-part ship, right? There's the command module and the lander module, and the International Space Station was also assembled in space as separate modules. Do you think that an interplanetary craft would likely be assembled in space before traveling?
So it really depends. So it really does come down to that mass fraction of how much payload do you want to send to the planet, right? So like with a lot of our lander probes, we're sending a ton or less to the surface of the planet, and that's with aerobraking when we get there. So you start to send humans, you're going to need, you send the actual humans, the food for their stay, and they're going to want to get back, so return vehicle. So you're going from less than a ton of useful payload on the surface to multiple tons, 10, 50, much larger. And so that means that you need to have your payload and dry mass for that and a proportional amount of fuel. So you're going to need a lot of fuel, and you can try doing that all in once and using staging, which is what the Apollo missions did. Staging increases your basically perceived mass fraction because you're shedding dry mass as you go through. Or you build it in orbit, you build a large ship, and you go to wherever you're going. And so there's different approaches. There's challenges with building stuff in space. There's also challenges of just building very large objects on Earth's surface and getting them into space.
And also you got to realize that the relationship between mass fraction and ISP and the delta V, which is your change in momentum that you want to get, that's an exponential relationship. So a really interesting example is the older version of the Cygnus cargo vessel. That could be launched from the Mid-Atlantic Regional Spaceport down in Virginia. It was, I think, like 3 meters in diameter, the Antares vessel. It was a small little ship in comparison to everything else. And now for the advanced Cygnus, which, with the larger pressurized storage area and with the larger solar rings and everything, they've stepped up from a small 3-meter Antares to a 5-meter Atlas V. And you know, like the radius and everything and the area, that's... So you can see that with the requisite change in mass, it's almost an exponential change in the amount of mass ratio you have available. So, you know, if we wanted to think about something like launching if we had to scale up launching like a softball worth of mass and try to scale that up to launching, you know, a beach ball worth of mass, it isn't going to be a linear change. It's going to be an exponential change in the size of the fuel you have to carry.
This might be a little off topic, but on like the topic of launch services, like when SpaceX launches Dragon, Falcon 9 is way overpowered for Dragon. I think Dragon weighs like roughly 10 tons with cargo, and with advanced Cygnus, when you're riding on Atlas V, there's way more payload margin on the rocket, and so you basically you kind of like make that trade-off as like we need this vessel of this shape, we need a rocket that can do it, and we can't do anything smaller. I guess we're going to lose some payload off the top. And so when you are in those kind of missions where you're going to Mars or, you know, some out of the solar system planets where you need all the performance, you basically need to design a vehicle that fits in with your rocket. And that, you know, you have certain diameter restrictions, certain mass restrictions, and it really complicates things.
So bottom line, there's not going to be a one-size-fits-all launch vehicle. It's going to depend on the mission itself in order to have enough delta V, but also not waste too much.
And it isn't just delta V. If you want to go and check it out online, it's actually pretty cool, but search like your favorite rocket, then payload planners guide. And typically there's a chart in there called a C3 chart, or a C3 Peregrine chart or something like that. So C3 is a measurement of your total orbital and gravitational energy that you can, well, it's a measurement of your total orbital energy. That includes your kinetic and your gravitational, because think about it, it's a simple physics problem. You're a certain height array from the ground, and you're moving at a certain speed. So you have energy. And so you have this thing called a C3 chart, which allows you to say, okay, if I have this much mass, this is how much C3 I can get out of it. And that C3 comes into play about, you know, if you want to go to Mars, it's like 14 kilometers per second C3 that you need. It's stuff like that. You'll need to look this up. But you say, okay, what's my mass of my vehicle? Where do I want to go? What's my destination? And what is the requisite energy that I need to impart on the payload to get it there? Now, with some ideas, like the whole idea behind SLS, from what I've read, is, you know, it's great to build things in orbit, but the ISS doesn't have any liquids that are born off over time. So if I can do a single launch that has pretty much all my stuff in one place, and then I can dock my crew vehicle to it, or I can dock whatever I want to it as fast as possible using a different rocket, then great, I get the best of both worlds. I get a huge vehicle with a lot of fuel in it that hasn't boiled off, because boiled off is a big issue, and then I can go somewhere. And so that's kind of the dream that I've seen about that one size. There isn't a one size fits all, and we're definitely starting to push more and more the size of our upper stage as best as we can make it. It gets hard. It gets hard because it's all exponential. It adds up fast.
As a follow-up to that question, the third option is to just send basically a fleet of small crafts. Do you think that's ever going to be a viable solution to, like, instead of assembling onto one thing, you just send a bunch of tiny ships to a faraway destination?
So there's lots of challenges with that, mainly because you basically get into like quantized parts, where you need an engine that's at minimum this size, you need a tank that's a minimum this size. With tanks, the larger they are, the more efficient they are, because their internal volume increases and their structural mass, their surface area, doesn't increase as quickly. And so building a lot of small ships, it's not possible. There's a lower bound of like how big you can make a craft that has enough delta V with all the engines and sensors and computers and payload. And you do gain some efficiencies by making larger things.
Anthony, did you have anything to add to that?
I don't know enough on the topic.
Okay.
So.
When we're sending people live, in 100-year blocks or so, right? Average lifespan is like 80, but traveling to really faraway places can take 10 decades, 10, 20 years to get someplace really far away. So in the future, there's been talk of like having a big craft, I guess, with enough food and stuff to keep people operating until they get to the destination. But there's also been talk of cryogenically freezing people, basically putting them into a suspended state and then reanimating them when they get to the destination, so there's essentially no time lost. But there are problems with suspending people and the fact that if you don't exactly know how to bring them back, it's not as simple as freezing and thawing, because that doesn't always work. So
yeah, and human cells expand when they get cold, and this brain thing that makes us so smart at flying spaceships tends to die when it doesn't get oxygen.
Right.
Yeah, there's some problems. So humans mad, I remember reading a lot that says 2.3 kilograms per day per crew member. Which, when you actually think about how much food that is, it isn't all that much stuff. Like, if you try to go full efficient with that, with the kind of stress astronauts typically go through, their workout schedule, just the calorie and nutrition deficits that they accumulate over the day, I mean, it's pretty light.
Yeah, when you're floating around in space, people on the space station, like Scott Kelly was up there for a year, he had to work out a lot, because when you're floating around, you don't have those stresses. Like here on Earth, my body is working to keep me sitting upright in my chair. In space, it doesn't have to do that, so your bones decay, your muscles atrophy, and in order to maintain that, you have to expend energy, but then you have to eat more, and then
it's a mass trade-off. So the most cost-efficient solution right now is get people to eat stuff and make them work out. I'm seeing the 70-day studies come up and everything, where NASA is hiring people to lay in a bed for 70 days to see what happens, which is really awesome science. I got to admit. Like between the TRINS experiment and the 70-day studies, like, this is what basic research is all about. Like, hey, what happens if we just shove someone in a bed for 70 days, we record all their vitals and see what happens? So, it's just beautiful to see an experiment that's like, we have two TRINS, both of them are astronauts, both of them are with roughly the same amount of spaceflight in advance. We'll collect all the data, shove one of them in space for a year, see what happens. It's beautiful science at its core and basic research at its core. It's great. So the big question is, what is more worth it? It could be really cool to say, like, yeah, we're going to have cool cryogenic chambers and we're going to freeze them in carbonite and they'll freak out and everything. But here's the question. is it more mass advantageous or power advantageous? Because you also have to think about that. Power is super limited. Is it either more mass or power advantageous to freeze someone out and have all the crazy equipment required to freeze them in carbonite, or is it better to just say, screw it, I'll send you with some protein balls. It'll just be simple and easier. We aren't going to HAL 9000 anybody on the way out. So, yeah.
Power bars and ramen.
Yeah. So like.
Yeah, you sprinkle some fruit and veg in there, and that's technically food.
Yeah, for most destinations in the solar system, you can get away with bringing, the supplies you need for your people. But I think part of your question was, going outside the solar system where it's going to take, at minimum, decades to get to your destination. And the idea of a generation ship is brought up a lot. And
Generation ship?
Yeah, so basically where you're traveling a distance where the people who embark will all die before they get to the location. So they have to reproduce, and there's going to be multiple generations living on the ship before they reach their destination. And I actually had a really cool discussion with my friends about this the other day. And there's lots of technical issues, obviously, because you have to be pretty much a fully self-sustaining colony in space, which is not an easy environment to do that. And there's some ethical questions and some huge psychological questions as well. There's a show called, I will look up the show, but there's a sci-fi miniseries that basically takes place on a generation ship, and the social aspects of that. So there's tons of things to talk about that with generation ships and those challenges.
So, hey TJ, I just looked it up real quick, and I found, so I'm using trajectorybrowser.org.nasa.gov. If you want a good way to race your time at work, I would definitely recommend this website because it's awesome. You can essentially query planetary data and then get trajectories. And it'll give you your C3, which is what I mentioned before. It'll give you the list of total delta V that you need. And it'll even give you the time, like when you need to leave. So moles, we all generally know, we've seen a lot on television, it's about 7 months for a Hohmann transfer, and Hohmann transfer is as simple as you can get. This trajectory browser goes a little bit crazier. It actually does pork chop plotting, and it does analysis and Lambert solutions, which is a kind of more extensive method of orbital mechanics. But even to go to Jupiter for a minimum delta V round trip, a minimum delta V round trip of 5.4 kilometers per second comes out to about 9.5 years, with most of that spent in transit. Moles, everyone's probably seen the 3-year moles plan. Venus, I've seen everything ranging from a year to a couple of years for Venus because it's so much closer and so much more inclined. So imagine packing all the food that you need for a year, well, 3 years, just to do it. I mean, the mass adds up, and as we talked before, that mass to propellant requirement is exponential. It gets huge, and that's just Powerballs that somebody eats.
And there's efforts on the ISS and on the ground of developing those technologies to reuse and recycle as much as possible of what you bring, so that can take a certain percentage, couple percentage points off what you need to bring, which when you are talking about years worth of supplies is a bunch of mass saved.
Yeah, like you pack a bunch of water, but you don't have to pack all the water that you're ever going to drink. You just pack enough so you can drink it, and then they filter out your pee and into water, and pure water, so it's not gross or anything. But also take water vapor that you breathe out, condense that back into water that you can drink again.
And also with like CO2 scrubbing, instead of using chemical processes, supplementing that also with maybe some greenhouses or plants, and basically reusing that carbon, getting actual food out using free solar energy or grow lights, and then that kind of supplementing your food with that. But these technologies are very the principles should work, but we're basically just doing experiments for those right now. We don't have working systems. They're just finally growing a little bit of lettuce and a couple other plants in the ISS, which is amazing, but it's a far cry from a full greenhouse spaceship.
And even those aren't going to be fully closed. If you look at the ecosystem on the ISS, it's far from closed. And the
Closed how? What do you mean?
So closed is kind of like Earth, right? We poop and then we eat where we pooped, and then we eat the things and we complete the cycle. And the trees, they take up carbon dioxide and they put out oxygen. And you really don't have replaceable filters here on Earth, right? The outside does a really good job until we kind of came along of taking care of itself. Nothing is really added or gained. It just stays like a closed loop. But if we look at the ecosystem on the ISS, it's very much open. There's still a lot of things like the filters that all you guys mentioned that have to be replaced. You have spares. And here's the thing on top of that. These aren't perfect machines. I mean, I can't think of a single product that I use today that doesn't have a medium failure rate of maybe 10 to 5% every time well, most of them are lower than that, but, sometimes things just don't work.
And astronauts will have to rely on those for years at a time.
Yeah, and even with additive manufacturing, a colleague that I worked with one year, Andrew Owens, he did a really cool analysis of what if we 3D printed, what if we had a fan break, and we need to replace a fan for the carbon dioxide scrubber on our Eclipse's environmental control and life support system. What if we had to print out a fan to replace it? The mass savings happen a long way down the line. It's hard. It's hard to make something that is safe, that is closed, that is reliable. So
I have a question related to this. Do you think that these limitations we're discussing are a product of just how interplanetary travel works, or do you think it's based on where we're at technology-wise? These are the limitations, and in the future there are potentially ways where these might not even be the issues we're worried about.
So traveling through space is a very unique environment that humans don't have a lot of experience in. So if you look at Earth migration, traveling over land, eventually over the oceans, you have resources around you that you can utilize that helps supplant what you bring with you, right? The people who crossed on the Mayflower had air,
yeah,
right? They didn't bring their own air on the trip.
And when they landed, they had trees and ground and
exactly,
yeah.
Exactly. So you can kind of live off the land as you move across it. With space, those distances are much farther apart. And also, it's very hard to get resources from your environment. That's why asteroid mining is a very interesting thing, because if you can get some resources along the way, then you don't have to bring everything at the beginning. Now, the trajectories of planning that and doing a path that lets you utilize resources on your path to your destination is very difficult, but that's one way of making this whole journey a lot easier.
Right, so we're planning to go to Mars in the near future.
Probably.
Where do you think is the next place humans will go?
Asteroids.
Do you think we're going to send people to asteroids before we send people to the moon, or?
Oh, wait, I thought... Well, it depends on which advisory council or committee report you listen to. So, one of the big discussions is Moon Force, then Mars, or Moon...
Yeah, we already had a podcast on that, actually.
Yeah, it's all over the place about destination versus technology-driven approaches. Take your pick. Moon is cool and everything. It's got water and everything, which could be used for life support. We've talked about this before for a wide variety of things. So living on the moon could be fun. And you could make some cool stuff on the surface of the moon, which would be good for industry. That could probably continue to grow the community. Venus is awesome. I'm a little bit biased towards Venus.
I want to talk about that with you in a future episode.
Well, I'm just an intern sometimes. That's all I am. I could get you in contact with the rear guys, maybe, but that could be cool.
That'd be fun.
But, I don't know, asteroids are pretty useful. You can develop industry out of it. You get an idea of what the primordial solar system was like. Some of them are tiny worlds in and of their own, like Ceres, 975 kilometers in diameter. Diameter. I'm going to double check that. So yeah, I'd go there probably. Yeah,
TJ, how about you?
got it right.
Yeah, Mars has a lot of benefits of why we should go there first. But once we have the technology to send large amounts of mass and people to Mars, we have that basically tool belt that lets us go to these places. So setting up bases on the moon is completely feasible once we have that. Going to asteroids is super feasible. So then it comes down to like what environments do you want to go to first? Venus, with the Cloud City proposal, is a really innovative proposal, but the surface of Venus is really like a rough place to live. The pressure is extremely high, temperature is really high. And then, with Mercury, you have one side that's extremely hot, one side that's very cold, and it's not the best place to go. And so I would probably go out to the moons of Saturn and Jupiter. Those have a couple places that are not terrible for humans to be on. You still have to bring a lot of the resources with you that you need to survive, but they're very interesting. Places like Europa and Titan would be interesting second steps.
Let me reframe my question a little bit. How long do you think it'll be before we have sufficient technology to get to the outer solar system, to send people to the outer solar system? Meaning like the moons of Jupiter or Neptune or something like that. Like rough. Based on where we're at now, decades?
I have no idea.
Centuries?
I just hope we go to the moon and we find like an old crashed like alien spaceship there, and like the engine's still intact, and we just rebuild a whole bunch of that. That'd be good.
That'd be ideal.
Like we land on the moon and we're walking around and we see like a crashed space Corvette, and we can walk up to the space Corvette and everything and like take all the good bits, and if the aliens want a proper burial, we be respectful and everything, but we take all the cool stuff. Like any good Skyrim or Dungeons and Dragons run, like be respectful but take all the cool bits. I got no idea.
Yeah, it's really, really hard to say. I mean, we've had this promise of Mars 20 years in the future for the past 40, 50 years. So, it's much easier to think of it in my opinion, in like stepping stones. Like once we send a person to Mars, that's one huge achievement. Once you send a large amount of people en masse to Mars, and then you have that skill set, that opens up a lot of different opportunities. So there's all sorts of political and financial, forces at bay, of whether we can actually go out and do these things. But once we have like the actual ability to, then we can find the will and the path, and then that comes with the timeline.
And if you want to get into the public policy sides of things, John Kingdon, you need a proposal, which is what we're talking about today. You also need a public to support it, and you need a politic that also supports it. And that's when you can make fundamental policy change. So, I would say that's when it will happen.
That's a great point. I want to end. I think we'll wrap up soon, but I want to end it on this last question, which I'm hoping to do pretty much every episode, and that's, what are some of the main things that we can work toward now in order to progress this technology into interplanetary travel? Like, what if I wanted to say, I'm going to make this happen, I'm going to put people on Europa, where should I go first to have the biggest impact?
Okay, so I'm going to say start studying, or if you know somebody who's really good at that, get them a pizza once in a while and support them.
Studying what?
Whatever they think is appropriate. So I've been trying to choose grad schools all this past week about trying to decide like where I want to go and what I want to do. And honestly, I would love if someone just bought me a pizza and said, come to my school, and then I know where I can help out them. No. So Support them. Go do internships. Go, like, I don't know what our viewership is just yet. We need to get those demos, man. We need to see how we're ranking with those demos. I've been watching a lot of Newsroom lately, too. Anyways, go and study. Study what you're good at. Be excited about that. Donate to programs that you believe in and you want to support. Donate in messages that you want to support too. Like Planetary Society has one viewpoint, the National Space Society has another one, the Space Policy Institute has another viewpoint, International Institute of Space Law. You know, if you're crazy about SpaceX, go buy some t-shirts. If you're crazy about Orbital ATK, I think they have t-shirts. Go and buy those. Money does speak, but just getting people excited speaks a lot more. Go get telescopes. Look through the telescopes. Tell your friends to look through the telescopes and say, look, we could go stab it with our flag. How awesome would that be? I don't know. Oh, that's a big question. It's a huge question.
Yeah, I don't expect you to answer it fully. I just wanted to hear your point of view. What about you, TJ?
Yeah, so there's a ton of, policy things you can do as just a citizen and, supporting space and getting people excited in space. Like, if you're looking to get involved in space and contribute scientifically, there's so many different realms. So, like, there's obviously engineering and just pure science, but psychology, and then just there's so many different things. There's so many problems that we haven't even addressed yet, right? We're working on the big challenges, but there's 1,001 things that need to be done and working perfectly before we can get a person on Mars, and 1,000,001 things before we can go out to Jupiter and beyond. So find something that you think is interesting, and if you're very successful in that, then there's a ton of crossover between all the different fields of work and space. You'd be surprised.
Do what you love, and then figure out how can I use my skill set to, I don't know what the word is, to advance.
Advocate.
Advocate.
And seriously, like, I know a lot of people are saying, oh, but I love space, but I don't want to do math and everything. First of all, I'm going to say, try out math. I'm trying to be your drug dealer for math. Just try it once. I'll send you some derivatives. They're fun. First one's on no. But it's like, math is pretty fun. But seriously, it doesn't always have to be science and technology. The times that I've worked as an intern at NASA, so I'm not a representative of this organization, I'm not a representative, or I'm an advocate for sure. But I had roommates that was a film major. I had a roommate that was a math and physics major. I had a roommate that was a psychology major. I knew people in foreign affairs coming to work at places like NASA. Why? And it's something that we've all kind of discovered being part of SPECs, is that engineers are great, scientists are great, computer people compute really good, but you need a lot of different people to come together and build these things. One of the things that, yeah, we all build this together. What?
Scientists, math people, and everything, it's not the whole equation.
No, it isn't.
That was a pun.
Oh, God, Phil.
I'm going to the gym. Screw this. I'm out. Where's the off button?
I agree with you completely, though, Anthony. And that's a very inspiring message to have. And on your point about math,
it is all math.
all through high school, all through first 2 years at college, math sucks in my head. Like, I don't like it. This is so tedious and whatever. But there's a few things in math that clicked for me, and it changed my understanding of how everything works, and specifically calculus. So, like, a derivative is just a way to quantify how quickly something changes. And then if you take the derivative of a derivative, you can see how fast the change changes. And seeing how they're used and the different things you can do by manipulating different basic operations like multiplication and addition and subtraction. It just all comes together, and if you just give it a chance, it will change your life.
Yeah, but it is, yeah, and there's tons of different ways to get involved. If you're passionate about space exploration, just go out there, intern with people, bother the people who seem to be doing things that you like to do. Like if you go to your local science museum, or if you see some dude at a fair, and they're with the space people, like just go up and ask them questions. Like seriously, that's how the scientific community grows. One of the funny things, I mentioned those 4 people that I had as roommates my first year at NASA, as an intern, not as a representative. The funny thing is the film guy is a guy who's currently employed by NASA. Just saying. I just got accepted for an internship again, and I'm going into the space systems engineering field. But yeah, there's tons of ways to support it. And if you want to make money, go ahead and make money. If you don't do whatever you want to do. Just, yeah, it isn't always math. There's more than one way to do anything. Always find solutions.
Talking about it in general is really important too. So
yeah, that's
asking
what this
questions.
podcast is called, and you should get your friends to subscribe.
Hey, go ahead, TJ.
Yeah, but if you're not like a technical person, you don't want to do number crunching. Like if you're a really passionate writer, like writing a novel about space, The Martian, amazing book, amazing movie, and so like that's a way to help contribute to the cause of space exploration. If you're an artist doing, technical drawings are, interesting and informative, and that takes talent, but also doing, more inspirational, abstract kind of things that show the beauty of space, the possibility of space. There's so many options through not just STEM fields, but all the creative fields, and it just takes an interest that develops into a passion, and you'll find a way to express that passion through whatever skills that you have.
Yeah. All the problems of the world are going to be solved by someone doing something.
You're not wrong.
No, it's like everyone's like, I'm going to wait until the perfect moment. I've watched House of Cards. I'm going to scheme. And it's like, nah, just try something out, see what happens.
Yeah. And one of the most valuable lessons I've learned through my work experience in school and everything, and especially this podcast, is just if you're curious about something or you don't know what to do, just ask somebody. If they don't know, they can tell you who might know. If you can't, if there's a roadblock, like with us, we had no equipment. So we asked for microphones, and we got microphones because people believed in us and they saw merit in what we're doing. And if you're passionate about something like space travel, if you just ask somebody, how can I get involved, they'll have an answer for you, right? Why are you laughing, TJ?
I just enjoy that we didn't have microphones, so we asked for microphones and got microphones.
That's pretty much how it happened.
That is exactly how it happened.
And here's the other thing is, don't pretend like you know anything, because A, you're probably going to irritate the people who do know everything.
Yeah.
And B, you shut yourself down for learning. Like this past weekend, I'm trying to get into astrophotography. So I went to the local observatory night and everything, and I just set up my tripod. I asked if it was okay for me to like take pictures and everything. And I took like 48 different shots. So I set up an experimental series where I changed the f-stop, the ISO, and the shuttle speed. And I just took kind of test images of Sirius and Orion over and over and over again. And at the end of the whole night, this guy came up to me and he's like, oh yeah, so you're a real expert and everything. And I just looked at him and I'm like, I have no idea what I'm doing. I'm just experimenting. Figures the guy was like one of the old design executives for engineering at Kodak. And he was also the head of the local astrophotography program. So he just starts laying down like all of this sage wisdom about how to take pictures of the moon and how to like capture an ISS, which is actually an ISS, the ISS, which is passing over the moon on Saturday. And so he just starts laying down like all this sage wisdom, and it's like, oh my God. I'm like, can I take notes? And he's like, yeah, sure. And it's like, it's amazing. Like, don't pretend to know anything. Like, if anyone asks you if you know anything, just say, I'm the dumbest person you ever talked to, but I'm interested and excited. And they'll say like, I'm going to give you some books, and I'm going to give you some knowledge, and I'm going to teach you how to do. It's like, it's awesome.
I do that even for things that I'm relatively competent at, because there's always something to learn.
Yeah.
And you never know where new knowledge is going to come from, or who's going to teach you some cool trick that you've been using this one program on your computer for a million years, like Excel, and then somebody shows you can add groups that you can expand and collapse with the plus button on the side. And I was like, blew my mind. Yeah.
Yep. Be the stupidest person and take every learning experience you can.
All right, thanks for listening. We'll be back in a week or two with another discussion on space exploration, science, and technology. If you have questions for us about this topic or requests for another discussion, send an email to SPEXcast@gmail.com. If you want to hear more, consider subscribing to us on iTunes or with your favorite podcast app. All past episodes are available to download from our website. This podcast is made possible by RIT Specs, a space exploration student faculty research organization at the Rochester Institute of Technology. Special thanks to the Interactive Learning Grant Program for giving us the tools to promote student and faculty engagement outside the classroom. Our music is credit Kevin Hartnell. This has been SPEXcast. We'll see you next week.